بسم الله الرحمن الرحيم ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة وقنا عذاب النار. Today, inshallah, we'll be discussing the philosophy of statistics, science, and models. First of all, I'll begin with George Box's paper. He was famously known for quoting that all models are wrong and some work. So my interest really sparked from this field of study when looking at Thomas Kuhn's work, and along with Thomas Kuhn, Elliot Sober, and generally just thinking about why statistics are revered and how reliable are they. So today I'll be discussing George Box's paper, Science and Statistics, and we will go through this paper, see what he has to say, and look at work by another researcher named Nestor, who works off of his concept to a degree. And yeah, we'll see inshallah how things go from there. So, Bismillah ar-Rahman ar-Rahim. Aspects of scientific method are discussed, in particular its presentation as a motivated iteration in which, in succession, practice confronts theory and theory practice. Rapid progression requires sufficient flexibility to profit from such confrontations, and the ability to devise parsimonious but effective models, to worry selectively about model inadequacies, and to employ mathematics skillfully but appropriately. The development of statistical methods at Rothamsted Experimental Station by Ronald Fisher is used to illustrate these themes. There's something he said caught my attention here, which is rapid progress requires sufficient flexibility. So as things are becoming more and more rapid in terms of progression and technology today, definitely things must be looked at in a flexible manner, because if you are stringent, you're to a large degree fixated on the issue rather than the goal. Of course, not saying that issues do not arise when looking to achieve said goal, but the idea is that you are consistently looking to develop the model in this case and looking to answer critical questions that demonstrate a theory, proposition, and of course, solve a problem. So, introduction. In 1952, when presenting R.A. Fisher for the honorary degree of Doctor of Science at the University of Chicago, Alan Wallace described him in these words. He has made contributions to many areas of science. Among them are agronomy, anthropology, astronomy, bacteriology, botany, economics, forestry, meteorology, psychology, public health, and above all, genetics, in which he is recognized as one of the leaders. Out of this varied scientific research and his skill in mathematics, he has evolved systematic principles for the interpretation of empirical data, and he has founded a science of experimental design. On the foundations he has laid down, there has been erected a structure of statistical techniques that are used whenever men attempt to learn about nature from experiment and observations. This is interesting here. On the foundation he has laid down, there has been erected a structure of statistical techniques that are used when men attempt to learn from nature. Important distinction here between nature and man, which is very nice. I have a book by Fisher, and hopefully it addresses some points here. Sorry, I don't have a book by Fisher, but I have a book that quotes Fisher. So this is Quantitative Genetics. Quantitative Genetics by Falconer. Falconer in this book discusses how to quantitatively approach genetics, and of course, this is statistics heavy, right? So here we have, for instance, an equation that he quotes, and the exact quote here is Fisher's statistical tables, pardon me, the, the correlation between relatives on the supposition of Mendelian inheritance, the genetical theory of natural selection, average excess and average effect of a gene substitution, the theory of inbreeding. So quite fascinating. That's the first time when studying statistics and genetics I came across Fisher. And Fisher is, of course, extremely influential in psychological studies, particularly between and within subject studies. If you're doing an ANOVA analysis and you're doing correction work as well within the same data. So yeah, I agree there. Extremely influential person. I'm not sure if I have it here. I can share it very quickly on the screen. Page 424. Okay. All right. So yeah. So this is just in the introduction. Anyway, yeah. So that's the first time I came across Fisher. Just wanted to mention that. Right. So Fisher introduced by the title which he himself would have chosen, and not as a statistician, but as a scientist. And this was certainly just since more than half of his published papers were on the subject other than statistics and mathematics. My theme then will be first to show the part that his being a good scientist played in his astonishing ingenuity, originality, inventiveness, and productivity as a statistician, and second, to consider what message that has for us now. So, George Box apparently is using Fisher's work here to break down his claim that all scientific models are wrong, however, some do work. And I do agree with this 100%. And I will justify as we go, inshallah. So, aspects of the scientific method. A heritage of thought about the process of scientific learning comes to us from such classical writers such as Aristotle, Galen, Grosseteste, William of Ockham, and Bacon, Francis Bacon, English guy, who have emphasized aspects of good science and have warned of pitfalls. You forgot to mention Ibn Haytham. Ibn Haytham played a crucial and extremely influential role in the scientific method where observations and testing and experimentation lead to the result leading to a theory and the theory therefore leading to further developments. I've given a very simple explanation and I've applied Occam's razor. So for those interested, I have not read this yet. I've only gone through a couple of pages when I was looking at Tversky and Kahneman's work, which is Occam's razor. So Occam's razor is the idea that you cut and shave as much information in detail as possible to explain something. And you have different concepts such as probability, Bayesianism, Bayes' theorem, frequentism, that then expand, ironically, on what you shave down. So, yeah, statistics is extremely crucial for those who are looking to do an undergraduate or a postgraduate in neuroscience, cognitive science, psychology, genetics, any of the STEM fields is extremely important. And there are various versions of statistical methods, of course. Now, moving forward, iteration between theory and practice, one important idea is that science is a is a means whereby learning is achieved, not by mere theoretical speculation. So, science is not speculative. There is a rigorous methodology that must be applied. And evidence of this is history of science. The philosophy of history is an example of this because I agree with R.G. Collingwood when he states that history is a science of its own because we are trying to understand data from the past, things that have gone by, and to a degree that can be applied in science. So when I read a scientific book or I read a scientific paper, I wasn't there in the lab, I wasn't there on the field, I wasn't exchanging data with participants. I have next to no idea of what the realities were when the study was published and being conducted. What I do have is data, numbers, and previous theories that may agree or contrast with what I'm reading at the moment. So speculation does play a role, but not an instrumental role. The idea here is to have a rigorous approach. That's what distinguishes between a professional and an amateur. On the one hand, nor by the undirected accumulation of practical facts on the other, but rather by a motivated iteration between theory and practice, such as illustrated in A1. So, now he's giving us a brief breakdown. So, A, the advancement of learning. This is something we touched upon yesterday. What learning is, what does it relate to? There's disagreements on the definition. There is no fixed definition when it comes to the idea of learning. But we'll stick with not a behaviorist or even a organizational psychology definition that we were looking at yesterday. We'll see how it's defined as we go on here. The advancements of learning. A1, an iteration between theory and practice. Excuse me. And A2, a feedback loop. So, starting point here in this zigzag looking diagram is practice data facts is here. So you have a hypothesis that you formulate, and with that, the null hypotheses. Model that you are going to implement and employ. Conjecture, theory, idea. So these are categories that are being defined here. Then from here, there is a deductive journey we're going on. So what is deductive? I'll explain in a second. And then from here, there's an inductive journey, and then deductive and inductive, according to George Box. So induction is the idea where you have a pool of theories, thoughts, and data, and then you generalize it. Deduction is the opposite. So you have a general term, a fact, and then you break that fact into its respective parts, although at times not always strictly in respect to what's being broken down. Sometimes there are things that are borrowed from other schools of thought or other subfields or other interdisciplinary areas. So, to give a very brief example, if you are looking to study neuropsychology, right, and I want to look at attention and the vision system of human beings, there is a situation where I need to break down what vision is, look at the primate and non-primate systems, understand the evolutionary perspective, understand the non-evolutionary perspectives, and of course, along with this, understand the cortical structures involved, neural pathways that aid vision in man, and how attention, which is an abstract concept, is then manifested through studies and theories that are replicatable, obviously, and at the moment are workable. And those that have not worked in the past, what were the limitations and the pitfalls that they went through? So, this is the depth that one has to go through, right? So, after that, it has another diagram here. So, we have facts and then consequences of hypotheses and then error signals. Right. So, okay. So, if I've understood this correctly, facts are here, consequences of hypothesis, which goes through a deductive process. Error signal, so these are the pitfalls I mentioned earlier, and then induction. So we go from here, now we're here, and then modify hypotheses. Yeah, because there is new data being brought in, and that's what Elliot Sober speaks of, right? He states that how does evidence change? Sorry, Elliot Sober when he quotes Royal, that how does the present evidence update your belief or challenge your belief? And then modified hypotheses. So Hj replaces Hj plus 1. Right. So matters of fact can lead to a tentative theory. Deductions from this tentative theory may be found to be discrepant with certain known or specially acquired facts. These discrepancies can then induce a modified or some cases a different theory. Deductions made from the modified theory now may or may not be in conflict with a fact and so on. In reality, this main iteration is accompanied by many simultaneous sub-iterations. So I think before we move forward, it's important to know what iteration is. So we'll use dictionary.com here through Apple. Iteration is a repetition of a process or utterance. Repetition of a mathematical or computational procedure, yeah, I agree with that, applied to the result of a previous application, typically as a means of obtaining successively close approximations to the solution of a problem. Yeah, so this is what I was talking about a few moments ago, of the rigorous approach to said methods. Now, on this view, efficient scientific iterations evidently require unhampered feedback. The iterative scheme is shown as a feedback loop in A2. In any feedback loop, it is of course the error signal, for example, that discrepancy between what tentative theory suggests should be so and what practice says is so. That can produce learning. So it seems to me that George Box's definition of learning is very, very close to the behaviorist's perspective of learning. This is quite fascinating. I am going to take a note of this actually. Oops. Because what he's saying is that during the moment or period where you are in the so during the moment of the tentative theory that's been formed, okay, that suggests what should be happening. So you're using, for example, model A, and of model A, 1, 2, 3 should be happening. But at the same time, what is happening is probably 1, 2, and 2.5. So 2.5 could be an error or could be an updated belief or possibly another paradigm. So again, this is something that has to be tested and worked on. Hopefully, inshallah, I've understood this correctly. Now, just want to make a note of this. Right, okay. Bismillah ar-Rahman ar-Rahim. So, according to according to Box, right, George Box, it seems that yeah, so efficient scientific iteration iteration evidently requires unhampered feedback. So it has to be constant, which is very difficult because there are variables that can affect the coherence of behavior, for example, in animals or fish. Evolutionary biologists and evolutionary psychologists study behavior. There's always variables, so it's never really constant. Workable models and theories, but they're not objective and exact. So, so in any feedback, okay, loop, it is of course error signal so error signal is what it alerts one regarding a change is about to happen, i.e., altering maybe tendencies. Is there a tendency? Again, this is just a generalization. We're not exactly looking at a specific study or model, right? So we can underscore that when it comes to questioning this. So, simple let's see. It's going to lack inconsistency. The inconsistency that arises, right, between what tentative theory suggests should be, okay, what ought to be, should be, and what practice says is so, that can produce learning, that can produce learning, right? The good scientist must have the flexibility and courage to seek out and recognize and exploit such errors, especially his own. In particular, using Bacon's analogy, he must not be like Pygmalion and fall in love with his model. Who's Pygmalion? King of Cyprus, of fashion and ivory, statue of a beautiful man, loveliness of woman. Oh, right, okay. So, parsimony, okay, is an interesting statistic concept here. Parsimony, extreme unwillingness to spend money or use resource. Principle of parsimony, also law of parsimony, the scientific principle that things are usually connected or behave in the simplest or most economical way, especially with reference to alternative evolutionary pathways compared with Occam's razor. So Occam's razor is what we mentioned earlier. The scientific principle that things are usually connected or behave in the simplest or most economical way, especially with reference to alternative evolutionary pathways. Okay, since all models are wrong, the scientist cannot obtain a correct one by excessive elaboration. That's an interesting claim. On the contrary, following William of Ockham, he should seek an economical description of natural phenomena. Just as the ability to devise simple but evocative models is the signature of the great scientist, so over elaboration and over parametrization is often the mark of mediocrity. Hmm. So keeping things simple, not over analyzing. Yeah, it's a good thing to have in mind. Right, so worrying selectively. Role of mathematics in science. Okay, right. Worrying selectively. Since all models are wrong, the scientist must be alert to what is importantly wrong. It is inappropriate to be concerned about mice when there are tigers abroad. Hmm. The role of mathematics in science. Pure mathematics is concerned with propositions like given that A is true, does B necessarily follow? Since the statement is a conditional one, it has nothing whatsoever to do with the truth of A, nor of the consequences B in relation to real life. The pure mathematician acting in that capacity need not, and perhaps should not, have any contact with practical matters at all. In applying mathematics to subjects such as physics or statistics, we make tentative assumptions about the real world which we know are false, but which we believe may be useful nonetheless. It's a very honest claim. The physicist knows that particles have mass, and yet certain results approximating what really happens may be derived from the assumption that they do not. Equally, the statistician knows, for example, that in nature there are never that never that there never was, pardon me. Equally, the statistician knows, for example, that in nature then there never was a normal distribution. There never was a straight line, yet with a normal and linear assumption known to be false, we can often derive results which match to a useful approximation those found in the real world. Hmm. But I'm going to shut this. Right. It follows that although rigorous derivation or logical consequences is of great importance to statisticians, such derivations are necessarily encapsulated in the knowledge that premise and hence consequence do not describe natural truth. Interesting. Let's read that one more time. It follows that although rigorous derivation of logical consequences of great importance to statistics, such derivations are necessarily encapsulated in the knowledge that premise and hence consequence do not describe natural truths. It follows that we cannot know that any statistical technique we develop is useful unless we use it. Major advances in science, and in the science of statistics in particular, usually occur, therefore, as a result of the theory practice iteration. Hmm, true. A researcher hoping to break new ground in the theory of experimental design. Okay, what's going The researcher hoping to break new ground in the theory of experimental design should involve himself in the design of actual experiments. Right, so the researcher hoping to break new ground in the theory of experimental design should involve himself in the design. The researcher hoping to break new ground in the theory of experimental design should involve himself in actual experiments. Okay. Investigator who hopes to revolutionize decision theory should observe and take part in making of important decisions. An appropriately chosen environment can suggest to such an investigator new theories or models worthy to be entertained. Mathematics artfully employed can then enable him to derive logical consequences of his tentative hypothesis, and a strategically selected environment will allow him to compare these consequences with practical reality. In this way, he can begin an iteration that can eventually achieve his goal. An alternative is to redefine such words as experimental design and decision so that mathematical solutions which do not necessarily have any relevance to reality may be declared optimal. Fisher, a scientist, with these ideas in mind, let us see how Fisher qualifies as a scientist using, for illustration, some of the events occurring during his stay. Rothamsted. In 1919, Fisher had rejected the security and prestige of working under Pearson in the most distinguished statistics lab in Britain, and at the time certainly in the world. Instead, he took up temporary job as a sole statistician in a small agricultural research station in the country. He was already 29, and he later said that he was aware that he had failed at both the jobs, teacher and actuary, that he had so far attempted. So John Russell, director of Rotham, said later recalled, when I first saw him in 1919, he was at a job before deciding anything. I wrote to his tutor, Case College, about his mathematics. The answer was that he could have been a first-class mathematician had he stuck to the ropes, but he would not. That looked like the type of man we wanted. I only had £200 and suggested that he should stay as long as he thought he should. That should suffice. He reported to me weekly at tea at my house. It took me a very short time to realize that he was more than a man of great ability. He was in fact a genius. At the end of the year, Fisher, who had a wife and child, had used up twice the £200. By that time, he had been given a permanent post. Weighing the baby. For the theory practice iteration to work, scientists must be, as it were, mentally ambidextrous, fascinated equally on one hand by possible meanings, theories, tentative models to be induced from data, and the practical reality of the real world, and on the other, with the factual implications deducible from tentative theories and models and hypotheses. So he's saying on the one hand, you have to be engaged with the real world and be fascinated by meanings that are derived and models and theories that exist and that can be worked around with data to form a generalization and the real practicality of the real world, right? Because behaviorist theories are not strict. They occur in controlled environments, and human beings and animals don't always necessarily work in that way all the time. So, and on the other, with factual implications deducible from tentative theories, models, and hypotheses. Fisher had great interest in practical matters. For example, he begins Real Business of his book, Stats Methods for Research, Chapter 2, discussing different ways of plotting data. His first example is introduced as follows. Right, so figure Figure 1 represents the growth of a baby weighed to the nearest ounce at equal intervals from birth. He does not say this is any particular baby. Recently, I was fortunate to see the Fisher family records in which Fisher's own hand are recorded the weight from birth of every one of his 9 children, weighed by himself with the results carefully graphed. Comparison showed that the child is his second son, Harry Leonard, who was born 1923, shortly before first edition of the book. The next leg of the scientific iteration is hinted at as he goes on to discuss how best to plot the data so as to make a rough examination of the agreement of observations with any proposed law of increase. Interesting, I like that phrase. A rough examination of the agreement of observation with any proposed law of increase. Find the lady. The extraordinary extent to which Fisher's actual everyday experience was grist to the mill of his inductive mind is further illustrated in the famous opening lines of Chapter 2 of Fisher's book, The Design of Experiments. A lady declares that by tasting a cup of tea, she can discriminate whether milk or the tea infusion was first added to the cup. We'll consider the problem of designing an experiment by means of which the assertion can be tested. Fisher proceeds to use this example to explain and illustrate the basic principles of good statistical design. Hmm. There was, of course, a real lady. This incident happened many years before the book. It was written and just after Fisher came to know. The lady was Dr. Muriel Bristol, the algologist. What's the algologist? Study of algae. And she had declined the cup of tea that Fisher offered because he had added the tea first. Fisher declared it made no difference, to which she replied, "Of course it did." Her future husband, William Roach, who was close at hand, said, "Let's test her." They did. According to him, she made nearly every choice correctly. In this, she behaved similarly to the lady in the book who got one wrong. From soil bacteria to non-linear design. The tea urn was a great catalyst to iteration. Before, there each afternoon Fisher conversed with members of the scientific staff and with visitors and became involved in their problems, often with dramatic consequences. One scientist who came to Rothamsted about the time as Fisher and became his intimate friend was bacteriologist Gerard Thornton. It was he who first interested Fisher in improving the time-consuming dilution methods for making bacterial counts. This resulted in Fisher's pioneering work on nonlinear design in 1922, mentioned by Cochrane. Interesting. From cotton to extreme values. One of the early visitors to Rothamsted was Tippett, a matter of great practical concern, cotton research. A matter of great practical concern to him was the strength of cotton yarn. Since the breaking strength of a piece of cotton is the strength of the weakest link, he was faced with what we should now call the extreme value problem. Tippett had first studied with Carl Pearson and had earlier approximated the distribution using the method of moments. In cooperation with Fisher, problem was tackled rather differently. The authors note that the limiting distribution must be such that the extreme member of a sample of n from such a distribution has itself a similar distribution. Right. So the limiting distribution must be such that the extreme member of a sample of n from such a distribution has itself a similar distribution. So n is a sample limiting distribution of an extreme member. So you have the graph here, and let's say the extreme member here, outlier possibly. It itself has a similar distribution. So if that outlier was to then go through such a similar analysis, it would probably have itself a similar distribution. But here it doesn't say probably, it says it has. So that's a definitive statement there. Okay, this simple but remarkable insight leads to a functional equation which yields as its solution the basic limiting forms. Okay, interesting. From these forms, almost all subsequent work on the subject springs. The theory has applications in such different fields as the design of dams and the reliability of components. Wow. The theory has applications in such different fields as the design of dams and reliability of components. Wow, okay. Like so many of Fisher's brain children, this is now regarded as a distinct field of study. I will use for further illustration work that Fisher did at Rothamsted between 1999 and 2010, which began with a regression analysis and ended up with a complete and elegant theory of experimental design, which is still the basis for most statistically planned experiments. This work was published in a series of papers having the general title Studies in Crop Variation, number 1, 2, 3, 4, sorry, 1, 2, 3, 4, 6. Okay, we'll definitely explore that for sure. By 1919, 13 plots on broad bulk wheat fields had received 13 different treatment uniformly for 67 years. In Studies Crop Variation 1, Fisher begins by presenting a workman-like discussion which lasts for 12 pages. Of the responses to the 13 different maneuvers reviewed by his analysis of the broad bulk data. In particular, he concludes that there is really nothing like plain dung. It gives a high yield with no significant diminution of its effect over the years. Diminution means reduction over time. Yeah. Hmm. He then quite suddenly shifts from maneuver to mathematics, revealing where his analysis came from. In the next few pages, he introduces orthogonal polynomials, presents formulas for the calculation from equispace data, obtains the distribution properties of the coefficients, and shows how their significance may be judged. Without calling it that, he presents the appropriate analysis of variance which he has used in fitting fifth degree polynomials to the annual yields. Most interesting of all, he discusses the properties of the residual y and y dash from a fitted polynomial of any degree r. allowing us to see him in the guise of what some people now call a data analyst. Most interesting of all, he discusses the properties of the residuals y alpha y dash from a fitted polynomial of degree r, allowing us to see him in the guise of what some people now call a data analyst. Okay, interesting. Data analysis, a sub-iteration in the process of investigation, is illustrated here. Tentative model, inference drawn, tentative analysis, criticism received, tentative model considered again. That's the diagram here. Nice, not bad. In the inferential stage, the analyst acts as a sponsor for the model. Conditional on the assumption of its truth, he selects the best statistical procedures for analysis of the data. Having completed the analysis, however, he must switch his role from sponsor to critic. The apt christening of statistical criticism is due to Cuthbert Daniel. Apt. Okay. In the inferential stage, analysis acts as sponsor for the model. Conditional on the assumption of its truth, he selects the best statistical procedure for analysis of the data. Okay, I see where he's going with this. Having completed this analysis, however, he must switch from sponsor to critic. Okay. Okay, interesting. Having completed the analysis, however, he must switch from his role from sponsor to critic. Condition now on the contrary assumption that the model may be seriously faulty in one or more suspected or unsuspected ways, he applies appropriate diagnostic checks involving various kinds of residual and analysis. I like that. Okay, so far it's good. Let's do this here. You have tentative model here on the left, and then tentative model, right? Inference drawn to tentative analysis. And then criticism this way. Criticism. In order to conduct his analysis of the residuals from the fitted polynomials, Fisher obtained the following. The average value of v y minus y dash as 1 minus r, which is the coefficient, I believe, for residuals. The average value of v y minus y dash as a 1 minus degree r plus 1 over n theta square. The individual variance of the residuals yj minus yj dash for the 67 observations. The identity would be theta square is v average value yj, which is equivalent to vyj minus dash y dash j plus value of y dash j. So now isolating this, where j can be 1, 2 up to n. Approximate formula for the autocorrelations of residuals from a fitted polynomial of any degree. The average value of vy dash from 1 and 3 is theta square r plus 1 over n. Thus Fisher says if we want to have a small variance for y dash, we should keep r small. A demonstration of the value of parsimony, which is the opposite of Occam, so razor right, helping to justify his use of polynomials of only fifth degree. Fisher plots the variances vy1 minus y dash j, yj minus y dash j for the individual residuals against their time order j. So that's time order. J is representing time order. Right, okay. Because it's spaced out. And obviously this is to do with crops. Okay. Because of relation 3, the graph looked at upside down is also a plot of v y dash j. Using that, he notes the deceptive reduction of the average value of yj negative y dash j at the extremities of the scale and the corresponding increase of the average value of yj, and says it is a weakness of the polynomial form that the extreme terms should be much affected. Okay. Finally mentioning that overfitting and underfitting are both to be avoided. He uses a matching of theoretical and empirical autocorrelations of residuals to check when a polynomial of sufficiently high degree has been fitted. In particular, he compares theoretical and observed autocorrelations of residuals from polynomials of degree 0 and 5 to show the inadequacy of the former and satisfactory fit of the latter. So why is he limiting it to 5 degrees? Why 0 and 5? This application of serial correlation of residuals to the awkward problem of deciding at what point adequacy of fit has been achieved has great freshness and interest 55 years later. Okay, excuse me. Right, so these are all examples of his statistical contributions. Okay, let's check this one. Group theory, then we go to Right, so this is the last piece I'll be discussing here, and the reason for that is because this diagram adds more understanding, at least to me, at the moment. And yeah, Bismillah. So, from muck raking to group theory, Eden's potato data serve to illustrate the method of analysis of variance. I don't know, but Fisher appears to have had no hand in planning that experiment. The design is not randomized nor blocked, and its very deficiencies called for appropriate remedies. When Fisher's friend Gusset saw the paper he wrote to Fisher, the experiment seems to me quite badly planned. You should give them a hand in that. Fisher later notes Gusset suggesting that I should start designing experiments. This he proceeds to do. The iterative process, including the design aspect, is sketched in Figure B. Hopefully that is clear. So the true state of nature that exists, experiment design D1, leads to noise, which is natural in any data. And then noise, from that you receive new data, and then you have available data. So now you have to discern the data from new data to available data. Data analysis, and then you have error signal, consequences of Hj, time of hypothesis. I think that's what that means. Hj is time of hypothesis. And then from here you have induction, okay? And then so you take all of this and then you form a generalized conclusion. Modified hypothesis, which is now Hj in the moment plus 1. That replaces your initial hypothesis, and then you go back to deduction. So now you have to take the generalized conclusion you made and then go back to the process of the consequences of the new hypothesis Hj1, go through the inductive process again, and zigzag your way through. So as we see here, feedback loop in deduction, induction, deduction, induction, and the loop that goes with it in terms of the feedback loop. So yeah, that is very fascinating. Didn't know it came from one guy. So between 1999 and an iterative sequence occurred that went through three main stages, each leading logically to the next by interaction of theory and practice. The analysis of existing records led to the analysis of experimental trials, which led to the design of experimental trials. Interesting. Okay. There were different but interactive aspects of this development. We can see number one, sequential evolution of new methods in response to unfolding realizations of need. I like that. That's a nice way of terming everything. Sequential evolution of new methods in response to unfolding realizations of need. Number two, the persuading of practitioners to try the new techniques. Yes, that is very cumbersome in most situations. And three, the changing role of the statistician implied by the development. So now here's a breakdown of each point. Evolution, changing role. Yeah, okay, it's very lengthy. So yeah, I guess this to a degree answers many aspects, clarified my not clouded, but fairly blurred ideas of statistics and philosophy and the philosophy behind science. So yeah, here's another paper as well, just before we go, is called Robustness in the Strategy of Scientific Modeling. And here he also states all models are wrong, but some are useful. Okay. Again, he gives a tentative model, tentative analysis diagram, and gives a example here. And then sensitivity, robustification, and pair t-tests, posterior distributions of p theta over beta and y. Of differences theta for parent distribution having differing amounts of kurtosis parameterized by beta Darwin's data. Kurtosis, the sharpness of peak of frequency distribution curve. Right, okay. Sensitivity to kurtosis, justification of kurtosis, joint posterior distribution, joint prior. Okay. Trying to make sense of what's being shown here. It's 36 pages, mind you, so trying to see if there's more diagrams that we are familiar with. It's interesting time series analysis. I'm fairly familiar with time series analysis. Not fairly, sorry. Very, very, very basic surface level. Right, okay, well, alhamdulillah, that's the stream. Inshallah, you gain some value and see you on the next one. Assalamu alaikum wa rahmatullahi wa barakatuh.